Hello, everyone. My name is Matt. I'm a research software engineer at the University of Cambridge, working in the Institute of Computing for Climate Science. And today I'm going to be talking about a library that we've been developed through our collaborations with various institutes around the world, which aims to couple PyTorch ML models with Fortran. I appreciate this is quite a niche application of PyTorch. No one really wants to look at Fortran codes anymore, but I'm going to try to convince you that Fortran is still alive and well, and people are still using it, and they're using it on really important pieces of science. Okay, that's the sell for Fortran out of the way. So what are weather and climate models? They are very complicated multi-component systems. In the middle, we have this dynamical core, where we evolve various conserved variables like temperature, velocity, pressure in time. And they're surrounded by all these other components like precipitation, multiphysics, cryosphere, and they feed back to the dynamical core. It's a very high-level overview of what a climate model is. This is just the atmosphere. There are other bits like the atmosphere, the land surface model, the ocean model, loads of different complicated processes that need to be coupled together. Right, so we have this sphere, or our Earth, which we discretize into lots of cubes, but these cubes can still be about 30 kilometers in dimension. This is really, really coarse. So what we rely on are these subgrid processes called parameterizations, which allow us to resolve below the sort of scale of our dynamical core. The problem is that these are a really large source of uncertainty. So this is, for instance, this is just rainfall. We can't obviously model all the droplets in the atmosphere. We have to rely on these other models, which could be empirical, they could be numerical, they could be from data. So going back to my atmospheric climate model, what we're looking to do is replace one of these parameterizations with a machine learning model. So this could be for a few reasons. We can make use of the wealth of data that we have available to us. And also, we could also speed them up. Some of these numerical models are extremely slow to perform. So a machine learning model could arguably be a lot faster. So this is in contrast to many of the models that have been sort of in the news recently, like Aurora, GraphCast, GenCast, ForecastNet. These are end-to-end processes. We're not interested in doing this. Climate science is much more complicated than weather. We're getting there, but we haven't got to these end-to-end processes yet using data alone. So there are many challenges from scientific challenges, but I'm going to be focusing on the language interoperability today. So obviously, machine learning is often written in PyTorch. It's a great model, great machine learning framework. And we want to bridge from Fortran to these machine learning models. There are lots of codes that are written in Fortran, like codes in the Met Office, ECMWF. In Germany, there's Icon, WRF, etc. So there are loads of codes that rely on using Fortran. So we have developed this model this library called FTorch. So researchers, they develop and train their neural network models offline. And then FTorch provides an interface from Fortran into PyTorch. We see PyTorch as a Python front end to a very highly optimized C++ backend called libtorch. And with libtorch, we can bind it to Fortran very easily using the ISO-C bindings in Fortran 2003. So what we do is we provide a Fortran API to libtorch directly, and this abstracts all the complicated details from the user. So it's really easy to integrate with PyTorch from Fortran. All that users need to do is to output their machine learning models in TorchScript. There was a great talk yesterday about the deprecation of TorchScript, but it's fundamentally relatively simple. This can be run in C++ with libtorch, and we're good to go. So our approach is quite a simple one. We sort of bypass Python entirely, and we go directly from Fortran to libtorch. And we avoid all of the headaches that can arise in high-performance computing or clusters and etc. with Python, which I'm sure many of you know about. So what are the highlights? Our library is very easy to build and link. We've developed these tools which allow users to script models very, very quickly and easily. And one of the real highlights of this is that we've developed this really comprehensive example suite. So it works users through taking a very sort of simple examples to more complicated use cases. So it really handholds users through the entire process. We've got really good documentation, if I do say so myself, and it's free and open source, licensed under the MIT. We accept, well, we're open to many contributions from the community. So we've tried to emphasize both developer and computational efficiencies. So we use all of PyTorch's or libtorch's implementation under the hood, so it should be reproducible and future support to new features. So you can guarantee that you should be able to get the same results if you run Fortran, the models through Fortran, as well as running them through PyTorch. We also expose, or we use all of the Torch backends for various GPU architectures. And one thing you might be thinking of is that Fortran is very different to Python, and indeed it is. There's this headache with how arrays are expressed in memory. Fortran is column major language, C++ and Python are row major. So we avoid this whole headache by using the torch-strided accessor, which abstracts all of this away from users. We also have no copy access in memory, so there are no unnecessary copies, and indeed, with the torch tensor-strided access, there's no unnecessary transposes of data, which could lead to completely erroneous results. Right, so I'm going to skip over the torch script. I think most people know about torch script, but there is executorch, which might be, which seems to be superseding it in the next few years. There are two ways to do it, tracing and scripting, but yeah, it's relatively easy to do. I want to show a bit of Fortran code. So we bring our library in, use FTorch, then we declare our input tensors and output tensors. These have torch tensor types. We create some input data. This could be our density, pressure, etc. And we alias our input data with our input tensors. So everything has type input tensor within Fortran. We then load our model, which has been saved as a torch script format. We run our inference, and then we do some cleanup because Fortran is not Python, and we have to do some. It doesn't have garbage collection, and we have to do some reference, reference count, reference counts dropping. One final thing in the last couple of minutes is something that we've been working on the last few months is online training and autograd. This has been work that's been led by Joe and our team. So all of the work that I've talked about previously has involved running codes that have been, models that have been saved offline, and we're just running inference on them. But there might be some situations where we want to do online training. So there have been a few papers that have been released recently in the climate science community where if you train offline models and then put them into production, they completely fall over. Like they diverge over very, very long timescales. So there might be, there's a good reason to do online training so that we can kind of massage these brittle models over time. This avoids saving large volumes of data. You can just completely avoid doing offline training if you want to and just train as you go in your climate model. You don't have to convert between Python and Fortran data formats. And there's also a possibility to expand the loss function to include downstream model code. So this is something that we're really interested in doing, and we want to find some really good examples for that. Problem is, this is really difficult to do in most frameworks. So what we do is, again, we utilize a lot of the PyTorch's functionality. I'm running out of time, but Just to expand on this loss function idea where we have some downstream parameter, our neural network might output tendencies, things that we don't really know how to interpret. These are completely abstract quantities to researchers working in the field. Researchers are more interested in things like precipitation or radiation. We can really get a handle on these. So what we would like to do is have this model and chain all of our PyTorch operations, or like tensor operations, and types until we get to this final output. And with that, we can then backpropagate from this quantity through our model and refine our model over time. So this automatic differentiation has all been implemented in a similar way to what I've described previously. We've basically piggybacked off of PyTorch. We've exposed all the autograd functionality from Torch, the requires grad, backward methods, SGD, Adam, etc. One of the really nice things about this is that we've exposed mathematical operators that apply to Torch tensors. This makes it easy to write sort of expressive sort of PyTorch code within Fortran. And it's still a work in progress. We've got some stuff to do on the loss functions, but most of the building blocks are there. So just to summarize, we have developed this library called FTorch. This is really scratching an itch or trying to fulfill a need in the scientific community, particularly for parameterizations in the climate community. We've tried to optimize both computational and developer efficiencies. And we're exploring options for online training and automatic differentiation. If anyone has any scientific examples that they would like to, that they're doing in Fortran and they've kind of faced a blocker and they would like to use our FTorch library, please come and talk to me. And we're moving away from TorchScript. If anyone has any advice about how to do that, I'll be interested to hear.